All right, Unit 9, here we come. We got more quadratic functions. This time we are looking at graphing them. We're going to look at some other ways to solve quadratic equations if you can't factor, and a bunch of other fun stuff. In this particular lesson, we're going to focus on graphing quadratic functions. Let's jump right in. Now, we're going to start. Now, you notice that this is graphing quadratic functions. What's on the screen? Linear functions. Are we in the wrong thing? Did I write something wrong? No, I didn't. But what I wanted to do is I wanted to compare the function that we already know how to graph, which is linear functions. I wanted to compare some of the components of it to a quadratic. I felt like that was a good jumping off place. So in linear functions, we're the first kind of new thing we're introducing here is we're introducing the concept of a parent function. So a parent function, this is going to be a really important concept moving forward. It's going to be an important concept for here and for quadratic functions, and then I think, what are we doing next? Graphing some, we're doing some other things. Yeah, square root functions. And then when we learn even more functions in Algebra 2, and we do things like cubic functions, and we do exponential functions, all the things, if we learn the concept of a parent function early, it's really, really helpful. So what is a parent function? A parent function is kind of a template, if you will. Like when you have real life parents, the children don't look exactly like the parents, but they look kind of like the parents, right? You can tell that this one goes with that one, right? And so that's kind of the idea. The parent function is a template. So the parent function for linear functions is f of x equals x, or y equals x. It looks like this. It's got a y-intercept of 0 and a slope of 1 over 1, right? That's what the parent function, and we can manipulate every other linear function based on this. Like we move the parent function up or down, and we change the slope of the parent function, all that kind of stuff. We can do the same sorts of things with the quadratic. So the standard form for a line, this is not actually true. This is actually more like slope-intercept form, but I chose to kind of cheat and call this standard form because it compares better to the standard form of the quadratic function. So for the purists and the pedantic out there among you, I know this is not technically standard form. Standard form of linear function is ax plus by equals c, right? I know that, but the comparison is better. The type of the graph, we call it a line, right? We knew that before. It doesn't have any axis of symmetry. We can't fold it over this way or this way. It actually does kind of have symmetric. It does have an axis of symmetry. It's just a crooked one. And so, but for our purposes, it doesn't have any. The y-intercept is b from the standard form. And that's really why I chose to use this fake standard form, because that compares better, more directly. What is that? Oh, some new something or other. I don't know why that exists. There. Okay, you go away. All right, sorry. So let's compare that to quadratic functions. So turn that off and turn this back on. So for quadratic functions, it also has a parent. The parent for the quadratic functions is f of x equals x squared. So we learned in the last unit that, excuse me, that in order for something to be a quadratic function, it has to be that highest power of 2, right? And that specifically is what makes it a quadratic, is as far as the equation is concerned. The parent function looks like this. It has I'm going to go ahead and label this because this is something that's not on here. It has a vertex. Vertex is that point where it ends at the very bottom point on the parent function. If we flip it over, we'll talk about that later, right? But the vertex is right here, this point. The vertex is at 0, 0 on the parent function, right? The standard form looks like this. It looks like a trinomial, right? Ax squared plus bx plus c. We've dealt with that, and we've learned how to factor that, and that's going to come back into play again later. What this graph is called, this shape is called a parabola, a parabolic shape. To find the axis of symmetry, so what is the axis of symmetry? So we're talking about this line right here. So the axis of symmetry is right here. And in order to find the axis of symmetry, we use this formula. Now, the B here is this B, right? This one goes with this one. The A here is that one. So in order to use this axis of symmetry formula to find the equation of the axis of symmetry, you have to have your equation in standard form, which is going to be straightforward. In Algebra 2, we end up learning how to put things into standard form and vertex form and all that kind of stuff. But most of the stuff in Algebra 1, it's just going to be given to us in standard form. The y-intercept is always C. It's always that term by itself that doesn't have an x on it, right? And so there's no x squared, there's no x. The one that's just by itself, that's the y-intercept. Let's look at some examples and how we do what we do. So let's pull a graph and then an equation. So we're going to use a table of values to graph this equation, which is in standard form, right? It's y equals the x squared term, the x term, and the no x term, x to the 0, right? And then state the domain and range. I'll remind you what that means in a minute. The domain and range, of course, well, I'll remind you now and later. The domain and range are what x can be and what y can be. It's really straightforward how to do that. So doing a table of values, we need to pick what values we want to do a table of, right? So for our x and our y values, it can be helpful if we get the x part of that axis of symmetry, because then we can know what to do. So we're going to use that axis of symmetry formula to kind of figure out where the middle of our table needs to be. So the axis of symmetry formula, again, is x equals the opposite of b over 2a. So in this case, the opposite of b, open parentheses, where the letters are, just like we've always done with substitution stuff. So b is the number in front of the x term, just the number, right? Not the x, but just the number, that coefficient of the x term. So the a is that one right there, so we're going to put a 3 in here. Now we can just simplify this on down. Negative 6 over 6, so negative 1. So the middle of our graph is at negative 1, right? I'm going to kind of move this over. I'm actually just going to shove it down here. I probably should have written, oh, what is that? That's not what I wanted to do at all. Move this over. Thank you. Right? So our middle of our table is going to be negative 1. And something, whatever y. So I'm going to pick some other numbers around that. So negative 2 would be around that. And actually, let's move that down because I want one more. I'm going to use 5 points. That's usually a good kind of baseline of what we're going to do. So negative 3 and then 0 and 1. Okay, so we're going to plug each one of these x's in and get y. So I'm going to move this over. I'm kind of doing a bad job of placing things today, but that's fine. All right, so we plug a negative 3 in there. So I'm going to kind of convert this sort of to function notation. We're going to do y of negative 3. That way we know what we've labeled here. So 3 times 3 squared plus 6 times 3 minus 4. 3 squared is 9 times 3 is 27. So we've got 27 plus 18 minus 4. I'm feeling like I'm going to put that in the calculator. Probably do it in her head or by hand, but I'm going to shove that in the calculator at that. All right, so 27 plus 18 minus 4 equals 41. So we're already at 41, so we're way off the graph, right? So that one was useless, which means this one's going to be useless as well. I'll show you what I mean here in a second. We actually have to do less work than you might think. Negative 2. Let's plug a... Oh, that's wrong, isn't it? I was supposed to be doing negative 3. No wonder it was 41, because it's way over here. That's not right at all, is it? Is it, y'all? Because this one's still going to be the same, because a negative times a negative is a positive. But a negative times a positive is a negative. So that should be that, which means this is 9 minus 4, which is 5. That equals 5. I'll double check because I'm feeling like it's the afternoon and my brain is tired. And I will attempt to not make mistakes. Yeah, good, great. So that's 5. Yeah, that makes much more sense. All right, let's plug a negative 2 in there. 3 times negative 2 squared plus 6 times negative 2 minus 4. Negative 2 squared is 4 times 3 is 12. Negative 2 times 6 is negative 12. That's handy. Minus 4. So that is going to be negative 4 because 12 minus 12 is 0. Minus 4 is negative 4. Negative 1. And this is actually going to be the last one we're going to have to calculate. And I'll explain that in a second. Y of negative 1. So that vertex is what we're finding here, right? So 3 times negative 1 squared plus 6 times negative 1 minus 4. Negative 1 squared is 1. 3 times 1 is 3. 6 times negative 1 is negative 6 minus 4. So this is negative 3 minus 4 is negative 7. It's going to barely fit on my little graph over here. So this is negative 7. Now, we don't actually have to calculate these other ones, and I'll explain why. I'm going to write what they are. I'll tell you what they are, and then I'm going to explain what's going to happen. This is, if I plug a 0 in there, we're going to get negative 4. If I plug a 1 in there, we're going to get 5. Okay, so how do I know that? I know that because parabolas, quadratic functions, are symmetrical. If we fold them over, they're going to be the same. So if we have our middle point be that vertex, and we have the same difference on each side, so I'm going down 1 here, and I'm going up 1 here, I'm going down 2 here, and up 1, or excuse me, up 2 there, they're going to have the same value because symmetry, right? So that's handy. We don't have to wait. We just have to kind of calculate half of it. That's great. So let's go ahead and plot these points, and then we'll connect the dots, and we'll be done with this problem. So I'm going to start with our vertex, just because it's handy to do that. Negative 1, negative 7 is right here. And then negative 2, negative 1, 2, 3, 4 is right there. And 0, negative 4 is right there. And then we've got 1, 5. 1, 2, 3, 4, 5. He's kind of a skinny parabola, right? And then the other one, the other symmetrical point is right there. And so we're going to connect the dots. Now, this at the bottom, it's not going to, even though this one's kind of narrow, it's kind of vaguely important to note that this bottom of this parabola is not a V shape. So it shouldn't just come to a point here. We shouldn't have a point down here, right? It actually kind of curves at the bottom, right? Shift Control Z. Beautiful. Okay, so let's connect these dots on this one. Somebody's home or something. And I forgot to turn my notification sounds off. It'll be fine. There'll be a beep in the thing. All right, so let's look at something else. All right, we want to find the vertex, the equation of the axis of symmetry, and the y-intercept of the following functions. Now you notice there's no graph here. And this is very important. I cannot stress this enough. If you can solve the thing just using algebra, do it. Don't graph the thing. It's like when we were learning about slope, or we're learning about whatever. Don't graph it to find slope if you're given 2 points. Just use the algebra way. Do it the way that's going to give you the right answer. Don't graph something unless you have to graph something. It's a lot of trouble, a lot of extra work for nothing. Learn how to do it with algebra. So that's what we're going to do with each one of these problems. Okay, so getting the right layer here. All right, so let's start with this one. So find the vertex, equation of axis of symmetry, and the y-intercept of the following function. So the y-intercept of this guy is going to be really easy. The y-intercept of both is going to be really easy. The y-intercept is just c, right? So the y-intercept, now the y-intercept is a point, so it's 0, negative 3. Right? That's easy peasy. The y-intercept of this one would be 0. Y-intercept would be 0, 4. Right? Easy peasy. No big dealio. Right? That's no problem. Get that out of the way, take it off. Now we're actually gonna solve for each one of these kind of in reverse order. We're gonna find the equation of the axis of symmetry using that formula. So that formula, again, I'll just write it once for both problems down here. That formula, again, was x equals the opposite of b over 2a. So to find the equation of the axis of symmetry, we're going to do x equals, the opposite of b over 2a. So b in this case is 4. We're going to put a 4 right there, and a is 2. So negative 4 over 4, which of course is going to reduce, and the equation of the axis of symmetry is going to be x equals negative 1. This is axis of symmetry. You notice that this is an equation, right? It's a vertical line at x equals negative 1. So that's easy peasy, right? Now to find the full vertex, we're just going to find f of the equation of the axis of symmetry part. So to finish and find the vertex, we're just going to find f of that. So y of, I don't know why my y's like to look stupid sometimes, sorry. Y of negative 1 equals 2 times negative 1 squared plus 4 times negative 1 minus 3. Okay, so 2 times negative 1 squared. Negative 1 squared is positive 1. Negative times the negative is positive. So 1 times 2 is just 2. And 4 times negative 1 is negative 4. And then bring down the minus 3. 2 minus 4 is negative 2. Negative 2 plus 3 is negative 5. So the vertex, again, is a point, just like our y-intercept part. It is negative 1. That's the x part, right? X, x. And negative 5 as the y part. All right, let's finish out this other one. So to do the vertex, we're going to use this formula, right? Easy peasy. Not the vertex, the axis of symmetry. Axis of symmetry. Okay. X equals the opposite of b, parentheses where the variables are. It's important that we do that because that way we can remember to ka-chink if we have negative, negative, right? So that's important. So our b in this case is 6, this one right here. And our a is, oh, there's nothing there, negative 0. No, it's not negative 0, right? If there's nothing there, it's a 1. So negative 1, right? So equals negative 6 over negative 2. Negative 6 divided by negative 2 is positive 3. These won't always be whole numbers, or integers, I should say, but they are in both of these examples. They won't always be. They don't have to be. Fractions are numbers too. So the axis of symmetry is at x equals 6. So to find the vertex, we're going to find f of that number. We can even change it to f if we want. Change it to f of x notation. If that helps you, whichever makes more sense to you. To fully convert it over to f of x, changing the variables, or if you just want to switch to function notation using y as y of x. So negative 6 squared plus 6 times 6 plus 4 equals 6 squared is 36. So negative 36 plus 6 times 6, which is positive 36. That's nice, right? We like problems that end up pretty. Negative 6 plus 6 is 0, plus 4 is 4. So all that remains is to write that as an ordered pair, right? So our vertex is at 6, 4. That's easy peasy. And the next thing. So, does your quadratic have a maximum or a minimum? So, if a, that number in front of the x squared term, is positive, I'm pointing down here, but you can't see me doing it, is positive, up there, oh wow, my hand almost reached all the way, up there, look at that, is positive, then it has a minimum because the graph opens up. Right? And if it's negative, if a is negative, it has a maximum because it opens down. It'll look something like this. Let's look at some examples using that information. So, consider this function. Determine whether the function has a maximum or a minimum value. State the maximum or minimum of the function. State the domain. Oh, that reminds me, like way back, I totally forgot. Like here, maybe? No. Here. I didn't say the domain and range. Bad, Sean. Bad, Sean. So the domain is what x can be. So the domain of a parabola, it is going to be getting bigger and bigger and bigger and bigger and bigger and bigger. And it's going to keep on getting bigger. Now it's getting bigger kind of slowly. It's inching out ever so slowly, but it's going to continue to get bigger. If we could graph this for infinity, it would keep getting wider and wider and wider and wider and wider. So the domain of this function, let me switch back over to this color, change this. The domain of any parabola, unless it's a real world problem, you'll see that in the last example we do today. The domain is going to be all real numbers. Now, there's a lot of different ways to write that, but for the sake of what we're doing right now, that this is good enough. We could use interval notation or set builder notation or whatever else. Now, the range is what y can be. Okay, so the y in this case doesn't go forever, right? It goes forever up in this particular example, but it does not go forever down. It doesn't go past this point right here. So the range is y. It's going to be y because we're talking about up and down. Range is going to be greater than or equal to -7. And the domain and range for pretty much any parabola is going to be really similar to this. Again, unless we're talking about a real world problem, and then we might have some constraints that shrink the domain even further and all that kind of stuff. But we're going to do it. We're going to throw a word problem at the end of this lesson. So, yeah, going back to here, maybe. Yes, great, did it. So, state the domain and range of the function. So we're going to consider this, determine whether the function has a maximum or a minimum. Well, just looking at this, a is negative, so it has a maximum. So, if we were to graph this, it would look something like this, right? It's going to go open down, so it has a maximum. So that's the first bit. Easy peasy. Great. Now, determine, state the maximum or minimum. So where would that be? Well, it would be part of the vertex. It would be the y part of the vertex. So we're just going to use what is actually called the vertex formula. We're calling it kind of the axis of symmetry formula, basically, in this lesson, but it's often called the vertex formula. So we're going to use x equals the opposite of b over 2a. So let's plug in the numbers. The opposite of b over 2a. B is -4. See, this is what I'm talking about right here. Is we gotta ka-chink that, right? And turn that into +4 over 2a. A is -2. So 4 on the top and 2 times -2 on the bottom, so -4. So that's the x part of the vertex, but we want, for the maximum, we want just the y part. So we need to find f of -1 equals -2 times squared. I'm going to put a -1 in there. -4 times -1 plus 6. -1 times -1 is +1. Negative times negative is positive. So 1 times -2 is -2. -4 times -1 is +4 plus 6. That's kind of easier to think about. Like if you're doing this in your head, we got 4 plus 6 is 10. -2 is 8. So f of -1 equals 8. That is the maximum. 8 is the maximum place on this graph. Easy peasy. Now, we are expected to graph this guy. So we've already done one a whole lot like this. We're going to do another one a whole lot like this. Let's see. I think what I was intending to do was to turn this on. There we go. So we're going to graph it. We're going to do just what we've done before. So we're going to find that equation of the axis of symmetry. Equation of the axis of symmetry by doing x equals the opposite of b. You already have this a bunch. You probably have this on the page already, so I'm not going to rewrite the formula here because you probably already have it in your notes. So the opposite of 4 over 2a. Remember, it's a 1. Nothing there is a 1. So the axis of symmetry is that x equals -2. -4 divided by 2 is -2. So our table of values, x, y, our vertex, our middle one is going to be at -2. Let's find f of -2 to get that y part, right? Plus 4 times -2 plus 3. -2 squared is 4. 4 times, 4 times -2 is -8 plus 3. -4 plus 3 is -1. -1, so -2, -1, so right there. So let's go -3, -4, and then -1, 0. Great. So, and actually 0 is going to give us the y-intercept. So we can already just look and be like, that's a 3. And actually, well, no, I'm not going to say that. So that tells us that this one's also going to be a 3. Wow. Making our life easier and easier all the days. Right? Let's find either one of these because it's going to give us the same answer either way. What do we want to do? How about -1? Because that's going to be easier. F of x, f of -1 equals -1 squared plus 4 times -1 plus 3. -1 squared is 1. 4 times -1 is -4 plus 3. Excuse me. So we've got 1 minus 4 is -3 plus 3 is 0. This one's 0, which means this one's also 0. That's nice. So we've got x-intercepts here and here, which actually, well, yeah, we'll talk more about that. We'll add those the layers that were cranking in my brain and all the things. We'll add those layers soon, or in a couple years, or something. Right? So there it is. Good enough for government work. Connect the dots with a bit of a curve. Again, this is not an absolute value function. It kind of curves up. Right? If I had, I don't think Photoshop has a mirror tool, but if it did, then using some sort of mirror tool or something would be a great way to be able to draw that quickly. All right. So let's turn these off and do one more example. I promised a word problem. Here it is. The cheerleaders at Blue High School launched t-shirts into the crowd every time the fish, what a great mascot, score a touchdown. The height of the t-shirt can be modeled by the function, that one, where h of t represents the height in feet of the t-shirt after t seconds. Graph the function. At what height was the t-shirt launched? What was the max height of the t-shirt? When did it reach the max height? So now, this particular problem, you notice that there aren't axes on here. We're gonna add the axes because this problem, like a lot of real world problems, this problem restricts the domain differently than normal, right? Because for this, I think it's gonna be easier to see. We actually really only want quadrant 1 because, and we really actually don't care about anything below the y-axis, below the y-axis, or below the or below the x-axis or below the y-axis. Now, in this case, they're not the x and y-axis; they're the h of t axis and the t axis. right? So we're actually only interested in a certain portion of this graph, right? Because time can't be negative, so we can't go this way, and we're not gonna we'll assume that these t-shirts are not gonna crash through the floor and go down into the underworld or something, right? So it's gonna be somewhere in this space, right? That's what's gonna happen, right? So excuse me. We're going to take a look at this function, and we're going to start by graphing it. We're going to graph it just the same way that we've done in the past. So let's grab our function. So yeah, that's what I thought. For h of t equals negative 16 t squared plus 48 t plus 6, right? So we can actually answer one of those questions. Well, we'll explain that. Let's not put the cart before the horse. Let's move on here. So to graph this thing, we're gonna do just like we've always done. We're gonna start by finding the vertex. Basically, we're gonna use x. Actually, in this case, it's not x, is it? T equals. So the maximum time, we know it's a maximum because this is negative, which makes sense because it's if we were launching it, would go right. Is the opposite of b over 2 times a. B is 48. Okay, so 2 times negative 16 is negative 32. So we've got negative 48 over negative 32, which I believe in my head I know that this is going to be 3 halves, but let's double check. 48 divided by 32 equals 3 halves, or 1 1/2. I am going to write the decimal equivalent. I know that I shy away from that, but in a word problem like this, that's often what we want to do. So we've actually also answered another one of these questions now with what we just found out. T equals 1.5. Now let's find h of t. So h of the height at time 1.5 seconds. Being after, seconds. Negative 16 times 1.5 squared plus 48 times 1.5 plus 6. I'm going to, especially since I'm using a multi-line calculator, I'm gonna plunk this all in here. So negative 16 times 1.5 out of the parentheses squared plus 48 times 1.5 plus 6 equals 42. Nice whole numbers. Well, not whole numbers, but fairly clean numbers. So if we're going to make us a little table, we're going to have time here and height here. And our vertex is going to be at 1.5 seconds and 42 feet, right? So let's kind of decide what scale we're going to do, because I don't think we're going to want to count by ones, right? That's not going to make any sense. That will leave us in some trouble, right? So let's count on the x-axis. Let's count by halves. So let me zoom in, make our life a little bit easier. Okay, so let's label this as 0.5 and 1.0. And we'll scooch over here and label this as 2.0, 3.0, 4.0, 5.0. When we come back out, is that visible? Yeah, that's totally fine, right? Easy peasy, lemon squeezy, right? So on this axis, I think let's count by fives, I think. So, oops. boy. Let's label this by 5s. So this is 5, 10, 15, 20, 30. We're skipping one, and then 40. And we'll go ahead and label 50. Right? We know we don't need anything higher than that, right? Because we just found out our highest number is at 42, right? So now we've got our axes labeled, and so let's see if we can figure out some other points. Let's at least get a couple other points and see what's going to go on here. So we know that the h of t intercept, the y-intercept, is at excuse me, is at 6. So 0, 6 is going to be one of the things. So when are we back to 6 over here? That'll be the same distance. So going back 1.5, going 1.5 this way, probably need to actually switch. 1.5 plus 1.5 is 3, right? So it's going to be 3, 6. So let's start kind of plotting some of these points. Again, how do I know that it's 6? Because the one by itself is the intercept. So we've got this point right here, and then at 3, 6 is right there. Right? And then we've got 1.5, 42, so about right there. So this is they're launching it up high, at least at this scale, right? And they're going way up here. And that. Now, let's, and smack somebody in the face, right? Something like that. Let's take a look at what we're asked for and see if we have enough information to answer it or not, right? So what are we asked for? So let's see. Let me kind of play with some colors here. So after t seconds, graph the function. We did that. At what height was, At what height was the t-shirt launch? Well, we know that because that would be at time 0. So at time 0, it's at 6. So height of launch is at 6 feet. Because that's the y-intercept. Easy peasy. Done did it. So what next? What is the max height of the t-shirt? We also know that already because that would be the y part of the vertex. So the max height is 42 feet. And when did it reach the max height? We also know that as well because that would be the x part of the vertex. So max height, this, at 1.5 seconds. So there we go. We've got a good enough graph and answering all the other questions. That is it for this lesson. It's a little bit longer one. They won't all be this way in this unit, but this is a long one. Hope you made it. Have a great day. Adios. Goodbye.